Suppose we want to find dy dx of y equals x raised to the x. If we think over our derivative rules, we realize that none of them apply. If we want to use the power rule, then the exponent must be a constant number, which doesn't work here. And if we want to use the exponential rule, then we need a constant in the base, which doesn't work here either. The issue here is that pesky x in the exponent. So let's bring it down using natural log. I can do that as long as I apply the natural log to both sides. So we have that natural log of y equals natural log of x to the x, which by log rules is the same thing as x times natural log of x. If we want dy dx, we can just use implicit differentiation. On the left, we take the derivative of natural log of y, which is 1 over y times dy dx. On the right, we have to use the product rule. For this, we have that 1 times natural log of x plus x times 1 over x is equal to natural log of x plus 1. So 1 over y times dy dx is equal to natural log of x plus 1. To get dy dx, we multiply both sides by y to get dy dx equals y times natural log of x plus 1. And since we know what y is, we can substitute that in to get dy dx equals x to the x times natural log of x plus 1. This technique of taking the logarithm of both sides to find the derivative is called logarithmic differentiation. It's a very special application of implicit differentiation, and it always follows the same pattern as we'll see in the next few examples. For example, if we want to find y prime for y equals x raised to the sine of x, we can take the natural log of both sides to get ln of y equals ln of x to the sine of x, which equals sine of x times ln of x. Then we hit both sides with d dx to get 1 over y times dy dx on the left, and with the product rule, we get cosine of x times natural log of x plus sine of x over x on the right. Notice that with logarithmic differentiation, the left side will always look like 1 over y times dy dx. Now we solve for dy dx to get dy dx equals y times the right-hand side, and when we substitute y equals x raised to the sine of x, we get a derivative only in terms of x. I want to point out that it's very important to apply the natural log to both sides of the equation. If you miss it on the right, you change the function entirely, leading to the wrong answer. One more example. Find dy dx for y equals sine of x raised to the tangent of x. Again, we don't have a way to find the derivative directly, so we have to use logarithmic differentiation. Taking the log of both sides, we get natural log of y equals natural log of sine of x raised to the tangent of x, which equals tangent of x times natural log of sine of x. Now we do implicit differentiation. Again, the left side is 1 over y times dy dx. On the right, we have a product rule, and notice to take the derivative of ln of sine of x, we'll have to do a chain rule. So then we get secant squared of x times natural log of sine of x plus tangent of x times 1 over sine of x times cosine of x for the right-hand side. Moving over the y and substituting, we get our derivative.